We were talking about white dwarfs in the realm of the ultra-relativistic. As we said, this is a problem because the kinetic energy and potential energy both go as 1 over r, and it's impossible to find a stable radius. Let's look at this a little bit more carefully. The transition takes place from non-relativistic to ultra-relativistic when the kinetic energy becomes equal to mc squared. So the question is, does the non-relativistic approach work for a 1 solar mass star? Or in other words, above what mass would this white dwarf become unstable? Let's set the non-relativistic equal to the relativistic. So in other words, let's write 3/5 gm squared equals 0.091 hc m over the mass of the proton to the 4/3. I can solve for m, and that will give me 0.091 5/3 hc over g, all this to the 3/2, 1 over the mass of the proton squared. Put all the numbers in, I'm going to get something on the order of 3.4 times 10 to the 30th kilograms, or about 1.7 solar masses. But the star isn't relativistic unless the kinetic energy is about 5 times 10 to the 5th electron volts. So what this is saying is, for a 1 solar mass star, the dwarf should be stable. Modern answer, of course, is the Chandrasekhar limit, which says that any dwarf that has a mass over 1.4 solar masses will not be stable. What will happen at that point is that you will have more a gravitational collapse, a supernova will occur, and then you will end up with either a neutron star or a black hole, depending on how much mass is left at the end of the supernova. So this is kind of interesting, but we can do the same sort of analysis for a neutron star. Let's do that. So instead, let's see if we can ask the same questions that we asked for a white dwarf and do them for the case of a neutron star. So for a neutron star, the number of neutrons, n, is equal to the total mass divided by the mass of a neutron. The kinetic energy, 3/5 times the n times the Fermi energy as before, which is going to be 3h squared over 40 times the mass of a neutron, the mass of a neutron to the 5/3, 9 over 4 pi squared r cubed to the 2/3. Potential energy, gravitational potential energy, going to be minus 3/5 gm squared over r. Same analysis as with the dwarf. And so what that does is when I look at the total energy, and this is non-relativistic, of course, E total is minus alpha over r for the potential, plus beta over r squared for the kinetic term. Alpha is 3/5 gm squared. Beta is, of course, this conglomeration of terms, which is really 0.028 h squared mass of the star to the 5/3 divided by the mass of the neutron to the, as it turns out, 8/3. So once again, I'm going to set the energy with respect to r equal to 0 to maximize the radius. what I'm going to get then is that my radius is equal to 2 beta over alpha in equilibrium. And that will give me, if I put it all together, it's going to give me 0.093 times 0.093 h squared divided by g times the mass of the neutron to the 8/3 times the mass to the 1/3. So as mass goes up, the radius has to go down. So for a 1 solar mass neutron star, R is going to be equal to 0.093 times Planck's constant 6.626 times 10 minus 34 squared 6.67 times 10 to the minus 11. That's big G. 1.67 times 10 to the minus 27, mass of a proton roughly. 1 solar mass is 2 times 10 to the 30 kilograms. That's going to give me something on the order of 12.3. So we would expect that a 1 solar mass neutron star would have an equilibrium radius of about 12.3 kilometers. Let's figure out the density. Density, of course, is going to be the mass divided by 4/3 pi times the radius cubed. That's going to give me something on the order of 2.6 times 10 to the 17 kilograms per cubic meter. Remember, we said before that density of nuclear material is about 10 to the 14. So this is even larger than that. My Fermi energy, again, non-relativistic, h squared, 8 times the mass of the neutron, 3n over pi v to the 2/3. And that's going to give me, I put all my numbers in, I will end up with an energy of 57 MeV. That corresponds to a Fermi temperature of, so this is going to be my Fermi energy divided by Boltzmann's, a Fermi temperature of 6.6 times 10 to the 10 Kelvin. So that's pretty large. Now, the actual temperature of a neutron star is much, much lower than the Fermi temperature. Now the question becomes, suppose it becomes relativistic. So in that case, my kinetic energy is going to be on the order of mc squared, which is about 940 MeV for the case of a neutron star. A 1 solar mass neutron star has an average kinetic energy of on the order of 34 MeV. So that being the case, it's going to be too small to be relativistic. So what we would expect is that the Fermi energy is proportional to m to the 4/3. So the critical mass would be larger than the sun's mass by about 28 to the 4/3 power, maybe a factor. So it should be about 12 times a solar mass before it's going to be relativistic. In reality, we know that a mass that's about 3 times the solar mass for a neutron star is going to ultimately collapse into a black hole. So there's a lot more physics that goes into that discussion. Well, these are just some of the applications that we have for Fermi-Dirac statistics. That, as you can see, they can range from anything from conduction electrons to really wild astronomical concepts. Next time, we're going to look at applications of Bose-Einstein statistics and then study black body radiation.